Okay, this is the notes for 1.3, and in 1.3 we're doing a lot of work on formulas and on writing formulas and equations given context and situations. Formula is any equation that uses letters to express relationship between two or more variables. So these equations can have lots of letters or just two letters, but there's got to be a relationship between multiple letters, multiple variables, and those letters are used to represent real values that we can measure and then put into the equations. The process of finding the equation and formula described real-world phenomena is called mathematical modeling. So when we create a model, what we mean in math is we've created an equation or a formula that allows us to predict or to describe the behavior of those quantities. Sometimes when we have those models, they're not accurate forever. If I wanted to calculate the number of lions in Africa, a model might work for a certain period of time, but either the lions are going to top out anyway, or maybe some other incidents happens where someone's killed several lions and the numbers no longer work for that model. And so we just want to be able to make sure that we understand these don't always work forever, but while they're working, it makes sense. And so an example of a mathematical model is excuse me, E equals 0.177t plus 71.35, which E is the life expectancy of U.S. women born T years after 1950. So in 1950, if I put a 0 there for meaning they were born in 1950, a woman was expected to live to 71.35 years. That was the average life expectancy for a woman in the U.S. But now, what if we change the numbers there? What if we allowed T to be 40? Okay, say for instance, if T equals 40, then we're talking about 1990. So 0.177 times 40 plus 71.35. If we test this for someone who was born in 1990, I'm going to put that in my calculator, 0.177 times 40 plus 71.35. It turns out the person's life expectancy is 78.43. And so in this problem, we know that we can go back and we can actually validate that. We could look at the life expectancy of a woman born in 1990 and see, is it really 78 years? Has it gone up by that much? Has it gone up by more? In the book, we learned that there's, in one of the model examples that they show, is there's actually a problem where they talk about by 2050 we could have people live as long as 200 years old. If that's possible, if that really happens, that's amazing. Medical technology is definitely changing. However, this may not really be valid in the year 2016. We may have to rewrite that equation based on women born after 2000. Maybe that's when another change occurred to the rate at which the life expectancy changes. But for the time that this worked, it was a great model, and maybe it still is. We'd have to look at the life expectancies now. When we do problem solving, there's a couple of things we want to really focus on. First, we need to let x be one of the unknowns or be the unknown. Then, this is the tricky part. We want to write all other expressions, all other equations for the other unknown quantities. We want to use x in terms of them. So, if I have the width is 2 more than the length, okay, if the length is my x and the width is 2 more than the length, which is x. So you see how we're only using x as our variable? As much as possible, we want to try to use a single variable. And then we would write an equation for the model that's given to us in text, solve it, and we always need to check our answer on these. We're building the equation, so we need to make sure that our answers make sense for the context. Okay? So let's look at a couple of examples. We've just got 3 of these. We'll kind of go through. The number of cats in the U.S. exceeds the number of dogs by 7.5 million. The number of cats and dogs combined is 114.7 million. Determine the number of dogs and cats in the U.S. So we're going to let x be the number of cats. So then if I took x minus 7.5, okay, it says cats are more than dogs by 7.5 million. So if x minus 7.5, the cats minus 7.5 million would leave us with the dogs. And so I'm going to say the number of dogs. Okay? The reason this is useful is because now if I take the cats plus the dogs, that's what this problem says right here, cats plus dogs, I should get the total population. And now it's a problem that I can physically solve. So this becomes 2x minus 7.5 equals 114.7. And then I'm going to add 7.5 to get 2x equals, it's a 7, 22.5. And we divide that by 2. And just make sure we haven't made any mistakes. 114.7 plus 7.5 is the 122.2. Sorry, I got focused on the 5. Yeah, it's a 2. It felt like there was something wrong. Divide it by 2, and we're going to get 61.1 million. And what was x? Well, x was the number of cats. Million dogs. If that's true, well, how many cats were there? Or sorry, that's cats. Cats. And it says that they exceeded the dogs by 7.5 million. So if I take this number and I minus 7.5, I'm going to get 53.6 million dogs. Okay? And so we found the cats, we found the dogs. The question we really need to ask at the end is, does it seem reasonable? Okay. We could have done x was the dogs and x plus 7.5 was the cats. There's definitely some flexibility here in the way we write our equation, but what's really important is when we're done, do these two numbers make sense? Do they add up to 114.7? Yes. Are the cats bigger than the dogs by 7.5? Yes, they are. Okay, so we move on to the next one. And we're told that we're going to inherit $16,000, but for the first year we need to put that money into savings. That's part of the contingency. Maybe our parents or our grandparents don't want us to spend the money right away. So we have to save it for at least a year. And so we put it into two investments. One pays 6% and one pays 8% annual interest. So we need to figure out how much should be invested in each rate so that we can get at least $1,180. Maybe we have a goal. We know that we want to buy a car that's worth $17,180 and want to know what will it take to get to that amount. And so, I mean, obviously if you invest all of it in the 8%, great. But a lot of times these things vary in rate, and they also vary in risk. At an 8% interest, you might actually have a higher chance of losing your money. So investment is really a tricky deal. We have to be careful with it. So we're going to let x be, let's say the amount in the 6% account. Okay, so if this was $5,000, then 16,000 minus 5,000 would tell me there's $11,000 left over. So this must be the amount in the 8% account. And so now what we need to do is we need to build an equation that makes sense for the problem. Whatever goes in here, we get 6% of it back as interest. And so 0.06 times x would be 6% of the interest plus 16,000 minus x. Sorry, we should probably I ran out of room. Okay. Times 0.8, that's my 8%, or 0.08, that's my 8%, has a total 1180. I want the interest from here and the interest from here to come up to 1180. The rest of the problem is about solving and then checking our work. So this gives me 0.06x plus 0.08 times 16,000 is 1280 minus 0.08x equals 1180. So I can minus the 1280 and I'm going to combine these two like terms to get negative 0.02x equals negative 100. I'm going to divide by negative 0.02, and x turns out to be $5,000. Lucky guess by Mr. Welch. Okay, so that was $5,000. The question though is, well, what would be the amount in the other account? So this was the 6% account, so the other amount would have to be $11,000 because we just subtract 16,000. So this was for the 8%, and this was for the 6%. Obviously, most of the money needs to go in that 8% to get a big increase in a year. And we can check those answers by taking 0.6 times 5,000. That comes out to 0.06 times 5,000 comes out to $300, and 11,000 times 0.08 comes out to 880. If you add the two of those together, you're going to get the 1180 that we were looking for. Last question. We have a rectangular basketball court is 44 feet more than the width. The length of the court here, and here's the width. We're told that the length is 44 more than the width. And so right now what I'm going to do is I'm going to say that the width is x. Then the length would be 44 more than means to add to the width, which would be x. So we have these two measurements. We're told that the perimeter of the basketball court is 288 feet. If you remember the perimeter formula, it's 2 widths plus 2 lengths. And so if 288 equals 2 times x plus 2 times 44 plus x, we should be able to solve this. Okay? This is 2x plus 88 plus 2x equals 288. I'm going to minus the 88 to get 200 equals 4x, and if I divide by 4, I will get x equals 50. So the question is, does that make sense? For this to be 50 by 94, is it 44 more? Yes. If I add it up, am I going to get 288? The answer would be yes there as well. So what are the actual dimensions? It's 94 feet by 50 feet. It is not okay to just say that x equals 50. The reason why is that wasn't the question. The question was, what are the dimensions? So please be careful to answer the questions appropriately, and we'll see you in class.